Welcome to this video on function analysis. In this video, we give examples and terminology about the ways that we speak about functions. Let's start by looking at functions that are increasing and functions that are decreasing. Here's a function, call it f, and the question there is this function increasing or decreasing? Well, I guess that depends on if you're reading it from left to right or right to left. In mathematics, we always have the notion that we're reading a function from left to right. And so in a left to right sense, this function is going up or increasing. But mathematicians aren't comfortable with loose definitions like a function is increasing if it's going up from left to right. Although we definitely want to think of it that way. But to be more formal, we're going to define what it means for a function to be strictly increasing. Here's a definition for strictly increasing. I'll pause while you slowly and carefully read it to yourself. Now, this may seem a little strange, so let me give you some visuals to go with this. Here's some random number on the x-axis, call it c. Here's a bigger number, d. So notice that c is lower than d. These 2 points correspond on the function to those particular x values. This value here is called f of c, and this value here on the y-axis is called f of d. This should be relatively familiar to you. We'll notice that f of c, the function value at c, is smaller or lower than the function value at d. And so this seems to match the definition at the bottom of the screen. Here's another example. Here's some random number c, smaller than d. Here are the corresponding points on the function to those x values. And here are their y values, f of c and f of d. And once again, with c being smaller than d, f of c was smaller or lower than f of d. Let's look at one more example. Random value c, random value d, corresponding points on functions. And once again, f of c is lower than f of d when c is lower than d. Now you saw 3 examples here, but the question is, will it always be true that the function f is lower than at c than it is at d, like you saw in those 3 examples? Well, if your function is essentially going upward from left to right, it will always be true. And so this definition corresponds to our intuition of what it means for a function to be going up or increasing. We call it strictly increasing. Now, mathematicians don't like wordy definitions. Our way of operating is to be as concise as possible, sort of built into our personalities. And so this definition transformed over the centuries. Mathematicians have sort of built a language of their own over the many hundreds of years that mathematics has been flourishing. And a mathematician wouldn't write this definition here. They would use this one. I'll pause while you analyze that. Now, it turns out these 2 definitions are the same. And if you're in a pre-calculus class, which if you're watching this video, you likely are, then the language at the bottom definition here may seem very unusual to you, but it is essentially the same definition as the more wordy one above it. Let's look at another function. Here's one. And let's analyze whether it meets the definition of strictly increasing. It does appear to be going up in some sense, but let's analyze the definition formally. First, by an example. Here's some random value of c smaller than d. Here are the corresponding points on the function, and f of c is less than f of d. So does that mean that this function is strictly increasing? Absolutely not. To be strictly increasing, it wasn't our job to find a particular value of c and d for which f of c was lower than f of d on the y-axis. The definition requires that every time we pick values of c and d with c being lower, that this condition hold. Watch the following example. Random value of c, random value of d. Here their function corresponding points, but it turns out in this case that f of c and f of d are equal. Can we say that f of c is lower than f of d? Not for this particular choice of c and d. But remember, for a function to be strictly increasing, the condition f of c less than f of d must hold for any choice of c and d where c is lower. But here's a choice of c and d for which that didn't hold. So this function is definitely not a strictly increasing function. And you can see that this condition, it may appear in red in the definitions. These conditions outlined in the definitions don't hold for this particular c and d. Notice in particular the one at the bottom, f of c is less than f of d. That's not true if f of c and f of d are equal. A number can't be less than itself. So you can see that this function fails to be a strictly increasing function. But mathematicians still had a sense that this function was, quote, going up as we read from left to right. It's not going downward anywhere, is it? And so mathematicians decided to make a new definition. See the word strictly here? They decided to take that out and just call this an increasing function. Now, even though it is constant or level for a decent portion of the middle of it there, as you can see the flat area, mathematicians still call it an increasing function. We just don't call it a strictly increasing function because it's flat, essentially, for part of it. So if that's what we want to think of as an increasing function, then we have to change the definition. So let's take out the word strictly and change a few things. We'll replace the word lower with no higher. That allows for the function to be flat. Or in the more formal definition at the bottom, we'll replace the less than symbol with a less than or equal to symbol. And this is our definition of an increasing function. By the way, it's worth noting, remember the function we saw earlier that was strictly increasing because it didn't have any flat or constant sections? That strictly increasing function also meets the definition of an increasing function. So a strictly increasing function is, of course, an increasing function. But conversely, not all increasing functions are strictly increasing, as we saw. By the way, a completely analogous set of definitions was created for decreasing functions. So we can define functions to be strictly decreasing or just decreasing. Here's an example of a strictly decreasing function. We could define it in a similar fashion as we define strictly increasing. Hit pause if you want to analyze the mathematical definition. Or if we took the word strictly out, we could call this a decreasing function and have a similar analogous definition to that for which we had for increasing. So let's take a look at another example. Here's a function. And just to give it a different name, we'll call it g instead of f this time. Not that that changes anything. I'd like to begin by posing this question. Is g of x increasing or decreasing? Well, it's not an increasing function, and it's not a decreasing function. In fact, most functions are neither increasing nor decreasing. Of course, this gives rise to some broader questions, such as, where is the function increasing? Because while it's not an increasing function in its entirety, it is increasing in parts of it in some sense. And also the question, where is this function decreasing? Because while it is not a decreasing function, there are in some ways parts of it where it is decreasing, at least on certain intervals. So let's tackle both of these questions by putting a grid in here, because if we're going to answer the questions of where, we're going to need some numbers. And we'll start with the question, where is the function increasing? Now, before I can answer that, I'd like you to follow me on this thought process. We're going to look for some x values here, and the question is this function increasing on the interval from 1 to 3? Here's the interval from 1 to 3. Here's the function on that interval. And the question now is that one portion of the function an increasing function as we read it from left to right? Well, I think it's pretty clear that that one piece of the function is an increasing function in its own independent right. And so the answer to that question would be yes. Now let's think a little bit beyond that. This function not only increases from x equals 1 to x equals 3, watch the graph, doesn't it also increase all the way up until x equals 5? Now, while it's a true statement that this graph is increasing on the interval from 1 to 3, we're going to say, as the answer to the question, where is this function increasing, we're going to say the interval from 1 to 5. Because when we ask the question, where is the function increasing, we want the largest, most inclusive possible interval on which that function is increasing. So while it's true to say that it increases on the interval from 1 to 3, the largest interval we can choose to make that statement true is that it's increasing on the interval from 1 to 5. Now that's interval notation, which most professors prefer. It is more the tradition, although you may also see an equivalent form of the answer, stating that it's increasing on the all x values between 1 and 5 as shown with the inequality notation there. That's not my preference, but you may see that answer from time to time. Now it's also worth noting that you may be asked when the function is increasing instead of where. These are essentially the same questions. When is an interesting word. Doesn't it imply a sense of time? When is something happening? I don't know, on Saturday. I don't know, between 4 and 6 p.m. These are the kinds of things we think about when we think about the word when. But because the x-axis in many scientific applications is also the time axis, the word when is the function increasing has crept its way into mathematics. So when you see the word when, we're not talking about time, we're asking the same question as where. By the way, it's also worth noting when you answer these questions, do not use y values in the answers to your questions. You can see on the interval from 1 to 5 that y goes from about -3.5 to maybe +2.5. If you don't see that, it's okay. The point is, we're never asking about the y values when we ask the question, where is the function increasing, or when is it increasing? Let's switch over to the question, where is the function decreasing? Again, we're going to want x values in our answer to this question. We'll look up at the graph on the left side. You can see in the beginning of this graph, as we read left to right, part of it has a decreasing aspect to it. In fact, given the fact that the x-axis goes forever to the left, couldn't we use negative infinity, not really a number, but as a symbolic representation of where this graph starts to decrease? And it would be fair to say that the graph decreases on the interval from negative infinity through 1. To represent that first downward portion, you may see it in orange. But look at the right side of the graph. Isn't the graph also decreasing anywhere to the right of 5? Or if we consider the fact that the x-axis goes on forever, we could represent that as 5 through infinity in interval notation. So because there are two separate intervals on which we can consider this function decreasing, we have, in some sense, two intervals in our answer. Now, to formalize this, we'll put a union symbol in between them, which is interval notation tradition to join two intervals into one set. And while that's probably the best answer to the question, where is the function decreasing, you might also see it in inequality notation as well. Again, not my preference, but we do see that from time to time. And recall that you're just as likely to be asked when the function is decreasing as opposed to where. Those are the same question. And also recall, do not use y values in your answer to the question. They're not relevant to the question of when or where a function is decreasing. Next, let's take a look at the concept of extrema. Here's a function. Let's call it h, just so we're not always naming our function f. But first, some vocabulary. An extreme point on a graph is a maximum or a minimum. When you see the words extrema, maxima, or minima, these are just the Latin plurals that we use in English. We don't say extremes, maximums, or minimums. Now on to the definitions. A local maximum point on a graph is a point whose y-coordinate is higher than or equal to any nearby point. For example, this point here is a local maximum because whatever its y value is, that's a higher y value than any nearby point. In essence, a local maximum is just at the top of a bump. You could think of it that way. Here's another local maximum. Why? Because that point is also higher or has a higher y value than any nearby points, whatever nearby means. This point is also a local maximum for the same reason. Its y-coordinate is higher than any nearby point. Now, I could give a more formal definition of a local maximum. And if you're in a calculus course, you'll have to deal with more formal definitions like this. But because the majority of students watching this video are probably in pre-calculus, it's better if we dispense with the formal definitions for now and just think of a local maximum informally as higher or equal to all nearby points. By the way, local maxima are also known as relative maxima, although I typically refer to them as local. A local minimum is similarly defined as a point whose y-coordinate is lower or equal to any other nearby points. So for example, this is a local minimum. Why? Because it's lower than any nearby points on the graph. Here's a local minimum for the same reason. This point on the far right is also a local minimum because it is lower than any nearby points on the graph. By the way, local minima are also known as relative minima. Let's now transition to something called absolute extrema, as opposed to local extrema. We'll start with an absolute maximum. An absolute maximum is a point whose y-coordinate is higher than or equal to any other point on the entire graph. So for example, this point here is an absolute maximum because whatever its y-coordinate is, we don't have any scaling on the axis to know what the y-coordinate is, but whatever that y-coordinate is, that is the highest y-coordinate on the graph, or at least tied for highest. This point is also an absolute maximum. They both are absolute maxima because there are no higher points on this graph. Absolute maxima are also known as global maxima, although I typically use the word absolute. An absolute minimum is similarly defined as a point whose y-coordinate is lower than or equal to any point on the graph. It's sort of the overall lowest point on the graph. Well, notice this graph has an arrow on this end and therefore goes down forever. And accordingly, this graph doesn't have an absolute minimum. There is no overall or absolute lowest point on this graph. Absolute minima are also known as global minima. Before we move on, it's worth noting that this point right here is both a local maximum and an absolute maximum. It's a local maximum because it is higher than any nearby point, and it's an absolute maximum because it is higher, or at least tied with, any other point on the entire graph, not just the points nearby. By the same logic, this point here is also a local maximum and an absolute maximum. Now, even if you have the understanding of what a local max and an absolute max and a local min and an absolute min are, one still has to be careful about how one answers questions and the way the questions are formatted. So let me give you some examples here. I'm going to put in a grid here so we can talk about these points numerically. Each space on these grids is considered to be 1. Here's the first question. Suppose we were told to name the local maxima of h of x. Well, here's one. If I were naming it, I would name it -1, 2, as we always name points. Here's another local maximum, 3, 4. And this local maximum is at 5, 4. So if you're asked to name them, then you name them as ordered pairs. That's not surprising. On the other hand, you may be asked, where do the local maxima of the function occur, or when do they occur? Well, they occur at x equals -1, x equals 3, and x equals 5. In other words, when you're asked where or when did the local maxima occur, we don't mention the y values. We simply mention at this x value or that one. Now, there's no additional information here, but it's a matter of formatting. It's a matter of how you answer the question, depending on how the question is phrased. Similarly, suppose you were told to name the local minima of h of x. Well, if you're naming them, then they're ordered pairs. Here's one. That's the point 1, 0. Here's a local minimum. That's the point 4, 1. Here's a local minimum, and that's the point 8, -1. So again, naming them is just a matter of listing ordered pairs. But if you're asked where do they occur, or when do they occur, that question is specifically asking you for x values only. So we say they occur at the various x values. Again, this isn't difficult. But you have to be aware of the way the question is phrased and the fact that that implies the way in which you might answer it. Now let's move from local extrema back to absolute extrema. We'll look at the absolute maxima of h of x. If you're asked to name them, well, there's two of them. This was an absolute maximum, and this was an absolute maximum. Again, you list the ordered pairs if you're asked to name them, or what points are they. And likewise, if you're asked where or when do they occur, you list only the x values. This is similar to what I've been saying on the last couple of screens. However, keep on the lookout for the question, what is the maximum of h of x, or find the maximum of h of x? Now, this can be a confusing question because when you're asked to find the maximum of a function, the first thing you might ask is, are you asking me for local maximum, or are you asking me for relative maximum? Absolute maximum. Well, in other words, what kind of maximum are you looking for? Well, the answer to this question turns out to be just the number 4. It's not a point. It's not referring to an x value. Because when we ask for the maximum of a function, we're asking for the highest possible y value. Now, this is a little bit confusing. Let me clarify. If we're asked for where or when, the expectation is that we'll find x values. But if we're simply asked what is the maximum or to find the maximum, we're being asked not for a specific point, but just the overall highest y value on the function. And the highest that this function gets is y equals 4. Now, the fact that it occurs twice at the point 3, 4 and 5, 4 is irrelevant to this question. This question is not referring to either of the absolute maxima. It's simply asking, what is the maximum value, meaning what is the highest y value this function attains, and that it attains that value of 4. And the fact that it attains it twice is not part of the question. Now, why don't they just ask, find the maximum y value to clue you into the question? Well, that's a fair concept. But it's just a matter of tradition. We refer to the maximum of a function as its maximum y value. And the same is true for minimum, by the way, but this function does not have an absolute minimum. If we were asked to name it, we would simply say there were none. You'll recall that this function has no absolute minimum point. And that completes the lesson on function analysis.